In this lecture, we're going to discuss a very interesting many-body quantum effect, namely the phenomenon of superconductivity, which is a rather amazing field because superconductors have a number of remarkable properties, such as, for instance, so shown here the phenomenon of levitation. So I'm showing a high-temperature superconductor wrapped up in a tissue to avoid heating, levitating on top of a magnet. And this phenomenon is actually unique in this form to superconductor, and it's based on expulsion of magnetic flux, so Meissner effect. So here I'm actually showing you a movie of the same effect, which was recorded by my experimental colleague Gian Piero Paglione in the Joint Quantum Institute. So and you here see a superconductor moving around on top of a magnet. So this phenomenon of levitation is indeed, quite remarkable, and is oftentimes used to impress visitors at various science shows, but it's just one of many exciting phenomena that appear in relation to superconductivity, and some of them we're going to discuss later today. But let me just mention that superconductivity is an extremely rich field. So suffices to say that it has so far resulted in about 10 Nobel Prizes that have been awarded for various discoveries in superconductivity. And furthermore, there are definitely a lot of major mysteries that still remain in the field. And obviously we cannot discuss everything in one lecture. So I'm going to focus towards the end of the lecture on a key theoretical concept that sort of underlies the theory, so-called Bargin-Cooper-Schiffer theory of superconductivity, and this is the phenomenon of Cooper pairing, which is responsible for, to a large degree, for the appearance of the effect. But let me start with discussing the main property of a superconductor, namely the state of zero resistance, which is also a reason why superconductors are actually called superconductors. And to do so, let me go back in time about a little more than 100 years ago to 1911, when this happy-looking guy, Heike Kamerlingh-Onnes, was performing various low-temperature experiments to liquefy helium. And during these experiments, he noticed that the resistivity of mercury dropped exactly to zero below a certain critical temperature of 4.2 Kelvin. So this was very surprising, and actually it is very surprising. It also should surprise you, in particular if you recall what we discussed in the fourth lecture, in the last lecture last week, where we talked about the resistivity of metals. And so I mentioned that in all real materials there always are imperfections that give rise to disorder, that in turn give rise to scattering and finite resistance. So what you would expect in a normal metal would be that the resistance can go down, but you would want it to saturate to a certain finite value. If there is no localization, if there is localization, it actually would shoot up and go to infinity. But there is no sort of reasonable sort of a priori reason why it would drop down to exactly zero. Not to a small value, not to a tiny value, to exactly zero. And this is what Kamerlingh-Onnes observed, and this was the birth of superconductivity. It was the first time people saw superconductivity, and it was truly amazing effect. And in particular, because of that, he was awarded the 1913 Nobel Prize in Physics. Now, another effect which already discussed in relation to this levitation was magnetic flux expulsion. This is probably a second very interesting phenomenon. And if you have a metal, let's say if you heat up this material up to room temperature, let's say, and penetrate it with magnetic flux, the flux will more or less just go through the material above the critical temperature, and there will be no significant distortion of the flux. So a sort of amazing phenomenon that happens once you go into the superconducting phase is that the magnetic field now tries to avoid the superconductor. So, and instead of going through it, it goes around it. And so you may say that it's expelled from the superconductor, and this effect is called the Meissner effect. So returning to this picture of a high temperature superconductor levitating on top of a magnet, what's actually going on here is that the magnetic field lines are sort of primarily go around this superconductor. And you may say that this superconductor sort of is sitting on this flux, because it's energetically not favorable for it to go down. It would increase the energy of the system, and therefore it's supported by this flux. Well, just a short comment here though is that I'm a bit oversimplifying this picture. So as a matter of fact, there's indeed this Meissner effect, but apart from the Meissner effect, there is also a little bit of a penetration of the superconductor by a magnetic field, but this penetration happens in the form of so-called vortices, which are, if you look at the, let's say, if you look at the cross-section of the superconductor, two-dimensional cross-section, and let me just plot it here. So there will be this superconductor, and most of this cross-section is magnetic field free, but there are certain regions which are very narrow regions, very small regions, where you do have a magnetic field sort of penetrating through very thin lines, and these lines are called vortices. So in superconductor, these magnetic field lines are called vortices, and these vortices tend to appear in the regions where superconductivity is suppressed due to various kinds of imperfections, a disorder that we already discussed. And this in turn leads to the pinning of this magnetic field line. So as a matter of fact, if you perform this experiment with a true so-called type 2 superconductor, which allows these flux lines, you not only would be able to see that it can be levitating on top of a magnet, you can actually turn it any way you see fit. You can turn it at any angle and it's still gonna sort of retain its position. And this actually even more impressive phenomenon is due to these flux lines and the spinning. But to discuss it further would be a bit going too far, so let me just stop here and say that all in all, so this magnetic field expulsion is responsible for this phenomenon of levitation. On a different note, interestingly, the Meissner effect, this expulsion of the magnetic flux, on the theoretical side is to some degree equivalent to the Higgs mechanism that occurs in elementary particle physics. I'm sure many of you have heard about the discovery of so-called the God particle or Higgs particle last year, but actually the mathematical theory of this Higgs mechanism in a different context of condensed matter physics was put together actually before Higgs by Phil Anderson, and strictly speaking I would actually call it Anderson-Higgs mechanism. I'm not going to go into details of why this expulsion of magnetic flux is equivalent to Higgs, but you may have heard that Higgs really is important in elementary particle physics because it gives rise to masses for some elementary particles. Here you may say that the Higgs mechanism in this form gives rise to a mass of the magnetic field, so it becomes energetically unfavorable for the magnetic field to be inside the superconductor. And well, this energy penalty for it to be there is sort of proportional to the so-called superconducting order parameter that appears below the critical temperature. So I already advertised the fact that superconductors host an amazing variety of various new phenomena, and the discoveries of these phenomena have in turn led to at least 10 Nobel Prizes, and I list here these major discoveries, sort of hallmark discoveries in the field. And the first one we already talked about. This is the Camerlingana's discovery of the effect itself back in 1911. Then John Bardeen, Leon Cooper, and Bob Schiffer got a 1972 Nobel Prize for developing a microscopic theory of superconductivity in the 50s. Brian Josephson and Ivar Jever got a 1973 Nobel Prize for discovering tunneling phenomena, various interesting tunneling effects in superconductors, in particular quantum coherent Josephson effect, so-called Josephson effect. We're not going to be talking about it, but it's very interesting. So these guys made a major breakthrough in the field. I'm going to mention it in the next slide by discovering so-called a family of high-temperature cuprate superconductors. Finally, just 10 years ago, Alex Abrikosov and Vitaly Ginzburg along with Tony Leggett, got a Nobel Prize, and in particular, these two gentlemen have put together a theory of vortices, topological excitations that appear in these quantum fluids. And I'm also including here a future Nobel Prize, which almost guaranteed to be awarded sometime in the future for a theory of these high temperature superconductors that I just mentioned. We don't really know yet the nature of these guys. We know they exist, we know a lot of their properties, very unusual properties, but what's really going on there, we don't know. So maybe it's going to be you, who knows. But you should hurry, because I think the new experiments are getting us closer and closer to understanding the sort of uncovering the mystery of these high temperature cuprates. In any case, what I want to emphasize here on this slide is a very large time gap between the discovery and the corresponding prize for of the first superconductor and the microscopic theory of superconductivity, which was put together about 40-50 years later. And it's not for a lack of trying. People had tried very hard and couldn't succeed. So it turned out to be very difficult to explain the basic nature of superconductors. Even though it took a while for the theorists to provide an explanation of superconductivity, the experimental work on this effect has never really stopped since 1911, since the discovery by Carmelianis. And the motivation for these experiments is really easy to understand. So as I mentioned, of course, superconductors are special in that they have exactly zero resistance. So they have no losses whatsoever. And they are able to conduct electricity with no heating. So if we were able to have a superconductor at room temperature, such room temperature superconducting wires would have been able to transport electricity over large distances with no losses. And this, of course, would have been great, especially now in the view of this looming energy crisis. Of course, now we transport electricity from where we produce it to where we use it using, well, normal wires, metallic wires, and those involve finite resistance and heating. And so this heat we just lose, so this goes nowhere. So to have a room temperature superconductor would be really great. But unfortunately, at this stage, we don't really know whether such a material may exist, whether it's possible at all. But there has been a lot of progress growing materials which have a much higher transition temperatures than the first 4.2 Kelvin superconductor back here. So this is the discovery of superconductivity. And this plot here is really a diagram. So here's the year from the early 1900s up to almost now. And the points here are correspond to compounds with the various transition temperatures. And so you see that for the first, let's say, 70 or so years, the progress has been really slow. But then in the 80s, there is a huge jump up to here, and this class of materials are what I already mentioned, the high temperature superconductors, so-called cuprate superconductors, which somehow dangerously, in quotes, close to room temperature, but they're not there yet. So they're close, but we still have about 100 Kelvin to go. Now, and also very recently there was a discovery of a new class of materials, so-called iron-based superconductors, or pnictides, that also look promising. But so far, all in all, this race to increase the transition temperatures in superconductors hasn't really involved much theories, mostly about experimental magic of growing materials and trying out different compounds. To emphasize this fact, let me actually, in the last slide in this segment, let me actually mention a guy who was really good at finding new superconductors. He was an experimentalist working at Bell Labs. His name was Bernd Matthias. And he was a legend in this business. And he, back in the 50s and 60s, he came up with a set of rules to help others discover new superconductors. And here I just list those rules. I don't expect you to understand their significance, and actually they're not to be taken too seriously, because in these high temperature superconductors most of those rules actually violated. But let me go over them. So he said that high symmetry is good, cubic symmetry is best. One should stay away from oxygen, stay away from magnetism, stay away from insulators. By the way, this is all we find in high DC superconductors. And the most important rule due to Matthias was to stay away from theories. And this was really bad, because but it was deserved, because again, for many years there was no theory of superconductivity. But fortunately, the situation has changed in the 1950s, when Leon Cooper and then John Bardeen and Bob Schiffer came up with a very clear explanation of the effect. And in the remaining 3 segments, we're going to go over this explanation, but in the next video I'm going to mostly talk about the preliminary material that we need to know to get there.